In this lesson, you will apply translations to quadratic functions and apply dilations and reflections to quadratic functions. So let's just review. A transformation is a movement of a geometric figure, and there are 4 transformations. A translation is a transformation where a figure is slid, we call that a slide, from one position to another without being turned. So for the translations you're going to have today, you're going to have movement left, movement right, movement up, and movement down of the parabola. Left, right, up, or down. Dilation is a transformation that alters the size of the figure but not its shape. So you're going to see that parabola either open up and become wider or compress, stretch, and become narrower. And we're going to talk about the words for those. And then a reflection is a transformation where a figure, line, or curve is flipped across a line. So that parabola is either going to open up or it's going to reflect and open down. So we're going to apply all of these 3 terms to parabolas. You won't see any rotations today. We're just going to focus on these 3. So as I said, there's 4 transformations. We're going to throw out the rotation, and those are the 3 we're going to focus on. So I want you to look and see how these graphs compare to each other. So I just opened up Desmos and I graphed all 3. So the red is x squared, just the normal parabola. The blue is an x squared minus 3. And can you notice how it's changed compared to the red? If you will look, this parabola in red sits right on origin, and look at where the vertex is of the blue. It's at 3, at positive 3. So even the equation here is x squared, like this, because I am adding 3, it moves up 3. So it's translating or sliding up 3. Look at what an x squared minus 4 does. I'm going to zoom out just a little bit so you can see. This is the green function. It's x squared minus 4. And if you'll look, its vertex is at negative 4. So if I add to the x squared, or if I subtract, it'll either move my parabola up or move my parabola down. So what I would like you to do is in your notes, look and see what the functions, graph them on Desmos, and compare them to the original function, which is the x squared. So I recommend graphing that x squared always first, and then you can look and see how the others compare. So I would say the x squared plus 3 is up 3, and I would say the x squared minus 4 is down 4. So you try the example in your notes. All right, now let's look at the next, which is a horizontal translation. So this is what you're going to see: movement left and movement right. So I went ahead and graphed all 3 functions. So the red is my x squared. Now look at this function. It's parenthesis x minus 2 parenthesis squared. If I subtract in the base, what's going to happen? Look at your blue graph. What's going to happen is, because I subtracted 2, it slides to the right 2. So if I subtract in the base, it's going to move right. Or in the case of the green, when I added 1 to the base, it's going to move it left 1. So you're going to see movement left or right when you add or subtract to the base. In the first example, we added or subtracted after the power of 2, and it moved it up or down. Well, now if you subtract before or add before the power of 2 in the base, it's going to move that function left or right. If you'll notice the blue one, I subtracted 2, but it moved right 2. So it's almost an opposite relationship. I subtracted 2, but it moved right. I added 1, but it moved left. So you can look and see how the examples, go ahead and graph them on Desmos, graph your parent function, and see how they compare to the x squared graph in your notes. All right, the next example that we're going to look at is when it does both, horizontal and vertical. If you'll look at this graph, I already know it's probably going to move right 3 and up 2. I can already know those patterns because we have already worked with the first 2 examples. We know what's going to happen. And I can hypothesize that this graph is going to move left 3 and down 1. But you can always graph on Desmos to see exactly what's happening. So I did that. I graphed all 3. This is my original in red, my x squared. Look at my blue. Did it do what I thought it would do? Did it move right 3 and up 2? It sure did. Here's right 3, here's up 2, and there's the vertex of that graph. So those patterns, if I'm adding or subtracting to the base, it's going to move it left or right. If I'm adding or subtracting after, it's going to move it up or down. Those patterns will always stay true. Let's look at the green. Do you remember my guess was that it would move left 3 and down 1? Look what it did. Left 3, down 1. That's exactly what it did. So you look at the examples in your notes. Go ahead and graph on Desmos if you'd like to. What we're going to look at next is a dilation. Now here's the language we're going to use. If the graph is wider, we're going to say it's compressed vertically. If the graph is narrower, we're going to say it is stretched. And you can think of that, if I'm stretching something, it's going to make it narrower because I'm stretching it out. The compressed vertically is going to become more open. So when we graph these, we can use that same language when we talk about what's happening to the graphs. So I graph all 3 of these functions. The red is my normal x squared. Look at what the blue did, the half x squared. Do you see how it is wider than the red? So we would say by multiplying by a fraction, it has made it compressed vertically because it is a wider graph. Multiplying by a fraction is going to make it wider. If you'll notice this green, it is multiplied by a 3 and it is narrower. So it is stretched. So multiplying by a whole number will make it skinnier or it'll make it stretched. This graph I am adding 2, so it moved up 2 as well as became narrower. So when I compare this to the x squared, it is narrower or stretched and up 2 because I added 2 to the end of it. So this one has both the dilation and a translation to it. So you can graph the examples where we're multiplying by the x squared, those dilations in your notes, and see if they become wider or narrower. All right, next up, what you're going to see is a reflection. If you'll notice before this x squared, I have a negative. That's a huge clue that it's going to flip the graph. If you notice before, I have a negative here as well. Huge clue, it's going to flip the graph. So I graph these on Desmos. My red is still my x squared. And look at my blue. I multiply it by a negative 2 and I subtract 3. So not only did it flip because it's multiplied by a negative, but I multiplied it by a whole number, so that made it narrower or stretched, and I subtracted 3, so it moved down 3. So this has a reflection, a dilation, and a translation. All 3 transformations right here on that blue graph. The green graph, I multiplied by a negative 4. What I did was I added 2 to the base, so that's going to move it left 2, so that's why you see it going left 2. Multiplying by a negative 4, that's a whole number, so it makes it narrower. And then I added 1, so it moved my vertex up 1. So this also has all 3 transformations to it. So you check the examples in your notes and see, use Desmos if you need to, see if those graphs reflect as these graphs did. Now, what we're going to do is try to figure out an equation from a graph. So here's a graph for you. Try to figure out what this equation would be. Well, if you look, my vertex here is 5 up. So I know I'm going to have an x squared where I'm adding 5. Now, what would you say as far as width here? Well, the width, it looks wider than a normal x squared graph, so I'm thinking there's going to be a fraction in front. And I also know that it has to be a negative because this is opening down. So I am going to put a negative fraction here. So here is the multiple choice that I'm going to give you. You have 4 options. I know that my in front has to be a negative fraction and it has to be adding 5. So this would be the correct equation of this graph because it's multiplying by a negative fraction and plus 5. I would only have chosen this if it was subtracting 5. So using those patterns can help you find graphs. So you try the example in your notes.